Before looking into the cosmos, we need to understand some aspects and limitations of the tool we will be using to do so. The human eye is constantly bombarded with rays of light, from which we can infer the nature of our environment. The human eye does not have infinite resolution. One way to determine visual acuity is to measure our ability to resolve vertical lines drawn close to each other. Here we have two instances of squares drawn with black lines on a white background, standing above grey squares. The black lines are drawn closer to each other on the right side. If you are close to your screen, it is easy to distinguish the line squares from the grey squares. However, as you move farther away from the screen, perhaps a few meters, depending on your screen size, this task becomes more difficult. Lines appear to merge together to form a grey square similar to the ones below. This merging will happen sooner with the square on the right side of the screen, as the lines are closer together. The distance where this merging occurs, and the distance between the lines, can be used in determining visual acuity. This experiment demonstrates two simple facts. 1. Objects that are farther apart are easier to resolve. 2. Objects that are closer to us are easier to resolve. In this graphic, the red circle represents the eye of the observer, looking at two objects represented by blue discs. The light rays leaving both objects are focused on photoreceptors in the eye. These rays are separated by a certain angle. This angle can be reduced by bringing the two objects closer together. However, we eventually reach a point where the angle is so small that the two rays are practically focused on the same group of photoreceptors. We lose our ability to resolve the two objects. They now appear as one. Another way to reduce this angle is to keep the distance between the objects constant, while moving them farther from the observer. Again, we reach a point where we are unable to resolve the two objects. The ability to resolve these objects depends on the angle made by the two rays. For the human eye, this varies depending on the observer and the conditions, but an angular resolution of 0.01 degree would be considered very good. Given that we are dealing with triangles, it is easy to calculate the angle made by the two rays from the ratio of the distance between the objects over the distance from the observer. On this graphic, the x-axis represents the ratio of the distance from the observer over the distance between the two objects. This value increases as the distance from the observer increases, or as the distance between the objects decreases. The y-axis represents the angle in degrees made by the two rays projected from the objects to the observer. We see that the angle drops rapidly at first, but more slowly as the ratio increases. Clearly, we must look at much greater ratios to reach the limit of resolution of the human eye. This is the same graphic, but showing a ratio on the x-axis going from 2000 to 8000. We now see the line crossing the point where even the best human observers will not be able to resolve the two objects. This happens somewhere past a ratio of 5000. Our ability to resolve two objects significantly influence what we see or don't see when we look at the stars. For comparison purposes, the Hubble telescope has an angular resolution of 0.000014 degree. For example, the polar star, Polaris, is a triple star system. The main star is Polaris AA. It has two other stars orbiting nearby. Polaris AB is at an angular distance of 0.00005 degree from Polaris AA, while Polaris B is at 0.005 degree. These stars cannot be resolved from Polaris AA with the naked eyes, but could be resolved by the Hubble telescope. We will come back to this issue of angular resolution when we discuss parallax in a coming video.